Section 4.5 as the title, Bases and Coordinate Matrices. In part, this is supposed to be a review that we have seen before. We will have vectors and vector coordinates in different bases. We'll also see how to change bases. First, we will look at some regular R2, R3 Euclidean coordinate system. And then we will also see how to use this in abstract vector spaces with different bases. So we saw examples for all these before, but this is a preparation for the next two sections where we will use these results for linear transformations. This is a very important section. It's not that difficult, but we will have some formulas that can be confusing. So as an introductory example, let's look at the two-dimensional Euclidean coordinate system. We have x and y coordinates. Usually we use the standard unit vectors. There is E1 vector, which is the 1, 0 vector. So 1 in the x direction, 0 in the y direction. And then we have E2, which is the 0, 1 vector. This could be used, for example, if you have a vector, say, -5, 4, then of course you know that this is -5 times 1, 0 plus 4 times 0, 1, or -5 times E1 vector and 4 times the E2 vector. And here we have the E1, E2 basis. It's called actually a standard unit basis. This is also called rectangular coordinate system. You have a right angle there. Yes, it makes sense to have this. But then, for example, this -5, 4 vector is in this direction. So then you might ask the questions that how does it make sense to use these two vectors for a vector that goes in the opposite direction? Furthermore, it might happen that you are working with a lot of vectors and all of them are pointing in pretty much the same direction. So then it's kind of strange that you want to assemble this -5, 4 vector with the E1 vector that goes pretty much the opposite direction, and then you have to use the -5 multiplier to reverse this direction and also expand it. Before we learn that any two vectors that are not collinear form another basis. So for example, we could have another basis which is more in this direction. Let's say we could have, for example, the -1, 1 vector, and let's say we leave one of the other vectors, the 0, 1 vector. Then this -5, 4 vector, if I denote here in this basis, for example, with U1 and U2, these two vectors, and let me use then, instead of set notation, let me use the list notation. This is supposed to be ordered. So this is a U1 vector, this is a U2 vector. Then these are more in the direction of the -5, 4 vector, and we get that -5, 4, how can we write this? In terms of the -1, 1, 0, 1 vector. So then the question is -5, 4 equals to some vector like C1 -1, 1 coefficient. So it's a linear combination of the two vectors plus C2, 0, 1. And as we have seen this before, we can create a matrix vector equation where we assemble these column vectors into a matrix. We collect the coefficient C1, C2 into a vector, and we write this -5, 4 vector on the right hand side, and then we solve this equation. This is, of course, we don't really need Gauss-Jordan elimination. It's easy to solve. C1 is 5, and once you have C1, we have that C2 is -1. So the idea is then that this 5 -1 could be used as a different representation of the same vector, where this means that we have 5 times U1 vector minus the U2 vector. And while this previous representation, the -4 representation, pretty much says that it's the opposite direction of E1 and it's 5 times as big as it is, and then in the direction of E2 and 4 times as large. What this says here is it's pretty much in the U1 direction. It's 5 times U1, and U2 may be negligible also. So this is the main part. Yeah, when you have big differences between coordinates, basically this suggests that the first component is the largest and the other components are smaller, negligible maybe. So this has applications, this changing the basis, for example, in numerical methods. So let's look at some theoretical arguments here. Here V is a vector space. We will use the notation V for vectors. B sub V will denote a basis with basis vectors V1, V2, Vn. It's important now that we will be working with ordered basis. It's an ordered list. And this V vector space could be abstract. We don't necessarily need a Euclidean vector space to look at things. Any vector V from this vector space can be uniquely represented as a linear combination of the basis vectors. So what we have is that V equals to the sum Ci Vi, I going from 1 to n, for some Ci from the field F over which we consider the vector space as I goes from 1 to n. And these are unique for each vector V. So then instead of writing this all the time, perhaps a shorter notation is to say that the V vector in this base B, V, have the representation C1, C2, Cn. So this is a vector, a column vector, basically an element of Fn, where you have n vectors in the field. Now in more general setting, we will see later that although this is only an n by 1, this is only an n by 1 column vector, but then of course we can also call this matrix, since it's an n by 1 matrix. So the definition that we call this the coordinate matrix of V with respect to basis BV. With respect to basis BV. So first of all, usually we have that the field is just the real numbers, and that means that we have C1, C2, Cn is a n vector of real numbers. And as we had this previous example before, using the standard unit vectors is probably not very interesting when you write this minus 5, 4 vector as a linear combination of the standard unit vectors. From here what we get is that if, let me use S now for this basis with the E1 and E2 vectors, then the representation of minus 5, 4 in the standard unit vector is minus 5, 4 using the standard unit vector basis. So what's so interesting about this? Or probably nothing. Maybe a better example, something I tried to emphasize already before. If we have, for example, polynomial 3 plus 4x squared in the vector space of polynomials over the reals, if you use the basis 1x x squared, let me use the notation b for this, then the polynomial has representation in this basis, which is the column vector 3, 0, 4. And the main idea is that if in practice we want to work with vector spaces of polynomials, that's kind of abstract. It's hard to use, for example, computers with polynomials. But if we convert this into a column vector of 3 numbers, 3, 0, 4, then there are a lot of numerical algebra computer programs, for example, to work with those vectors, matrices. So let's go back again to the general case where we have this linear combination of basis vectors. We looked at matrix vector multiplication before, and we also looked at this representation before, where we put together these V vectors into a matrix. Well, this is really it could be an abstract vector space. So really what we know now is that this is an abstract, possibly abstract 1 by n vector or matrix. And then we have the coefficients, which is a n by 1 matrix. So this is not necessary, but possibly abstract. But if you put this together, then definitely, yes, we have either a matrix or some kind of a vector, depending on what the structure of these V's is. So what we have here is two matrices multiplied together. And the first one is really the basis, the V basis, and the second one is the coordinate matrix. So let me write this down again. This is one of the main formulas in this section, that any vector can be written as the basis matrix times the coordinate matrix. So the basis multiplied with the coordinate matrix. So let's say now that we have another basis denoted by BU, because say these are U vectors, U1, U2, UN, in the same vector space V. So for these, this also holds that we can, for example, represent U1 vector as the BV basis times the U1 vector's coordinate matrix in this BV basis. This is actually true in general from I going from 1 to n. And then if you put together the U vectors into a matrix or row vector, U1, U2, UN, this is a 1 by n vector, then listing one after the other, these factoring out BV basis, what we get is that this is BV times putting together these coordinates, U1 coordinates in the BV space, the U2 vectors coordinate matrix in the BV space, and so on. So what we get here is that the BU basis can be written as a BV basis times a matrix A. And so this is a 1 by n vector. This is also a 1 by n vector. What we get is that A must be a n by n in order to match the sizes. So this already talks about how to go from one basis, how to relate one basis with the other, how to change basis. In fact, this A is sometimes called a transition matrix from base U to base V. And sometimes this is also denoted by T, that reflects to transition, TUV, or another notation that will be clear maybe later is I, which stands really for the identity matrix, and then subscript U, superscript V. And these are lowercase letters denoting the basis, the U and the V basis to the same vector space. So why is this so useful? The idea is that if you have, for example, V represented in the U basis with coordinates C1, Cn in the U basis, that means that we can write V as a linear combination, I going from 1 to n, Ci, Ui, which we also wrote before, the same as the BU basis, and this is a row vector, times the C1, Cn coordinate matrix. So if we then substitute this formula for BU, then what we get is that this is the V basis times the A vector times the coefficient C1, Cn, the coefficient matrix or vector. So these are matrix vector multiplications here, and the matrix vector multiplication is associative. Associative matrix vector multiplication means that we can rearrange the parentheses, and we can get that this is the same as BV times the A vector, A matrix times C1, Cn coordinate matrix, which then becomes the BV matrix. So this is a n by n matrix, and this is a n by 1 matrix. So what we get after this is a n by 1 matrix. That means we get d1, dn, and this is actually the representation of the vector in the BV basis. So my previous notation was wasn't perhaps the best. I better write just V vector equals to the linear combination of the U basis vectors. Or perhaps maybe write that the way we obtained this representation is that the U basis was multiplied with this V vector's coordinate matrix. in the U basis. So what we have is that if we have this BU second basis, and what we see from these multiplications, the matrix vector multiplications, that this is a basis if and only if A is invertible. And for this, we only need, for basicity, we only need linear independence since we have an n-dimensional vector space. So the important way to write this again, BU equals BV times A. Then A is called the transition matrix or change of base matrix from base U, that was BU, to base V. And what this equation here says is that if you compare this last part, so we have the V basis the same in these two cases. So what we get is that for any vector, the representation in the V basis can be written as A times the representation of the vector in the U basis. So this is perhaps a better explanation why this is called a change of basis from BU to BV, because if you know the representation in BU, then we can get a representation in BV using this matrix multiplication. So what's very important here is that the V basis is multiplied from the right to get the U basis, but actually it's kind of turned around, and to get the representation of vector in the V basis, we have to multiply with the A matrix from the left, the U coordinate matrix, or the coordinate matrix in the U basis. This will be used later, so we have to practice how to work with this.